If you have questions on the homework, then we can spend some time. Just send something in chat so I know whether we need to reserve some time to do that. And then yesterday we had made it up a little bit. We had a little bit of fun going through some slides of antennas and manhole covers and things like that. But today we're going to get a little deeper into the elements of wireless network. Most wireless networks today have high-speed fiber connecting the base station back to some central location. And there's a whole other world of acronyms and names they use that deal with how they separate the traffic. The other thing that's dominant in most of these towers today is they convert everything to IP at the base. They don't carry the phone calls back even as digital signals on a separate communications channel. They just use one and aggregate everything together. So with the phones that we have now, your voice is all converted to digital before it's transmitted. It goes up and down a stack similar to TCP/IP when it gets to the tower to be blended in with data packets that you're sending, which are not sent using the same exact mechanism very often, and they're combined nonetheless into a single IP stream. So when they get back someplace, the IP has to be split off from the data. And so there'll be a few diagrams that try to show you this, but it's not the focus of the professor and not the focus of the book, so we'll add some detail in since it has been a focus for me. One of the things that we use in a local area is Wi-Fi. So all of the 802 standards that you see here are all promulgated by the Institute of Electrical and Electronics Engineers, and they're the ones that maintain the standards for Wi-Fi. So if you want to actually manufacture something that is conformant to Wi-Fi, then the standards can come from them. They have nothing to do with licensing the spectrum, however, because that's retained by governments around the world. You know, it seems like this should be able to be zoomed in like a lot bigger. Should I risk, like, no, it doesn't like it. Zoom. How about this? Sorry, we're watching the screen in large shares. I'm amused easily, apparently. Yeah. Okay. Wow. Do I feel stupid? I wonder how many dozens of lectures I gave without trying that out. Something about you guys inspires me to like experiment. I don't know what it is. I think that's a good thing, probably. So, and then there's some other standards in here that are maintained and put forward, or the word that's used both in networking and computing and in real estate is promulgated. So these standards are promulgated by other organizations. What you'll notice about this graph is they show effective distances. And so we will usually use Wi-Fi down to here. You can up it and use some mesh technologies here if you want, but the Wi-Fi frequencies aren't very good at penetrating buildings, and so they don't usually do well inside to outside. So if you want outdoor, you usually have to buy outdoor rated equipment. And then most of this is commercial licensed exclusive domain of the carriers. So you can run things in what's known as infrastructure mode or an ad hoc mode. In an infrastructure mode, you're connecting your base station to the outside world, and there's handoffs. So one of the ways that cellular has been popular is they're constantly monitoring your signal strength, usually at more than one tower, and there's a system that's making the decision when to flip you over from one tower to the next. And it's based not just on signal strength. Ideally, you have a signal that can be managed by more than one tower, and if that's the case, then they can add other variables into the equation. Variables like the capacity available at the next tower, or the signal to noise ratio at the next tower, or the capacity to backhaul at the next tower, et cetera. Or sometimes they can do it based on whether they're going to have to pay someone, because you may be at the edge of a roaming agreement. And there's settlement that's done, like with the airlines. If one airline, and I don't know if this still works this way or not, in the old days, if one airline canceled a flight, your ticket would usually be accepted as a courtesy on any other airline, and you could get home that way. And then the airline that issued the ticket would owe them money for doing that. And so you would settle up at the end of the day the number of route miles you had flown each other's passengers, and if there was a balance, then you'd write a check to the other party. And that was done commonly. I've been on tons of flights that weren't the ones that issued the ticket. And in the cellular space, when you handle roaming for someone else, there's a fee structure that governs what you pay. Very interestingly, when I went to Germany, AT&T continues to be very aggressive and innovative in their plans. I think they view this, other than corporate networking, they'd love to get rid of their telephone network and just stick to wireless, because that's where the revenue is. And 3-4 years ago, when I started going to Mexico, I had the ability. I didn't have to pay for text and phone calls. Those were free. They weren't for people in Mexico, so they didn't have unlimited text and free phone calls until like a few years ago, because there was no competition. And at least I had that, but the data was not free. The data was extraordinarily expensive, so you basically turned it off. And I went to Germany maybe 3-4 years ago to Berlin for a conference, and I remember I was going to buy a SIM card for my phone, and between the time I got on the bus at the airport and got to the cellular store, I wasn't using anything other than a couple of maps. I already got a text from AT&T telling me I'd gone over $100 in charges for roaming. And I'm like, I'm on the freaking bus. I haven't even made it to the hotel yet. Are you kidding me? And so this time I went 2 weeks ago, and the plan now is I pay $10 a day, and I inherit my plan that I have at home. My plan at home now, from everyone, including AT&T, is they treat Canada, Mexico, and the U.S. as one area. And if you have free calls and free text, which all the plans do, you have it in all 3 countries. I also have unlimited data on my plan, and I get unlimited data in all 3 countries. So when I go to Mexico, I can turn on my Wi-Fi hotspot on my phone and watch DirecTV with no charge, as long as they want, because they now own a network in Mexico. So I was very curious what would happen in Europe, and when I went there to Germany, I paid $10 a day. You activate it instantly on your cell phone app that they give you. There's no more calling and week ahead and all this other junk. Nothing to sign, any of that garbage. And I had unlimited data, unlimited calls and texts in Germany. So if you look at what's happening in this industry, the thing that makes people sort of nervous is the revenue is basically doing this. It's not, I'm not really paying much more to get this done. I mean, they made another $100 out of me this month, but I did that on the bus last time, right? So it seems like a good deal. And in general, if you're working for a business where your costs are going up like this and your revenue is kind of going up like this, at some point these two are going to cross each other. And there's a word for companies that remain in that state for very long. It's called bankruptcy. And so you will go out of business. For, among other things, if you're not generating enough return, so there's a percentage rate of interest that you're able to return here and give back in terms of dividends to the share owners and pay percentages on bond investments. It's relevant to this class because network investments are huge. They're switches and data centers that are $1 million a piece. It's not unheard of. So if you don't generate enough investment, then Wall Street will stop loaning you money. So for every corporation, there's a percentage of return that they expect based in part on the risk. So if you're a low-risk business, then they're willing to accept a lower return because they're more confident they'll get it. Like with Burlington Northern Santa Fe Railroad, they're expected to generate about 9%. Last time I talked to their CEO, Matt Resen, they're expected to return about 9% a year. And it's really tough because out of $1 that they know they're going to make every year, 80% of it is already spoken for. So this 80%, and this is a direct analogy to carrier networks, the 80% goes to pay for keeping the locomotives up, maintaining the track, paying right-of-way, upgrading or replacing broken crossings, paying for the pension for the employees because it's still a union sort of thing, et cetera. So they only have 20% of their money that is not spoken for. And so this 20%, and this amount down here only makes maybe, I don't know, 5%, something like that. So it only makes 5, so they're under. They're missing by 4 points if they're supposed to make that. So this 20% has to make 9% for itself, plus the remaining 4% times the remaining 80. So you can do the math on it and figure out that whatever they invest in with this 20% has to make a return in the double digits, well into the double digits, 20, 30%. So if you want business with the railroad, you have to show up with something that is either going to cut costs or explode revenue by 20 or 30%. And if you don't, it doesn't matter if it makes money for them. If it's not making enough, they can't do it. So when you look at a carrier now, like Verizon, for example, or we can pick on AT&T again since they're based here in Texas. If you look at an AT&T, what they need is something, if this is the revenue line and this is the cost curve, and it's creeping up, they need something that will put downward pressure on these costs and open up this gap. So it's big enough that the CEO doesn't get fired by the board under pressure from Wall Street. So Randall Stephenson, the CEO at AT&T, like a lot of CEOs, was the chief financial officer before he became CEO of the company. He's not a communications guy. He didn't come out of operations. The last CEO, Ed Whitaker, was a communications guy. He started there climbing poles in like Kansas or someplace 25 years ago. He then, AT&T, after he retired, the CEO when it was going through bankruptcy. And then as a month, he's now the ambassador to the United States from Mexico, or the ambassador to Mexico for the United States. I think I said it backwards. There's no way the other one would happen. So these guys are skilled, but what you find in a lot of these now is that they're CFOs. So how does this relate to this class? When we talk about software-defined networks in particular, the reason why carriers are leading the charge is because SDN, despite the risk that it may offer and the huge development that still needs to be done to mature it, it does this to costs. So how many of you pay more for your cell bill this month than you paid a year ago? Yeah, maybe. How much more? Maybe you don't. So little. Maybe you're not really sure. Just Yeah. So I remember paying $550 a month cell bills when we used to travel to South Texas for a phone company, working on a high-speed network that we were trying to get deployed for a school district down there, gifted, talented students. They had no advanced placement classes, so we were trying to hook them up as a demonstration to the state of Texas because regulatory relief to put high-speed networks in more places. So we connected them back to the High School for Health Professions in Houston, where they had tons of advanced placement classes, and we taught students down there. And they got into better colleges, and they got better jobs, and paid more taxes, they bought bigger land, and paid, right? So it just kind of gets the whole thing going. And I remember paying these huge bills. That doesn't happen anymore. So the costs only can be improved if you, the revenue can only be improved if you offer new services. Think about what's been going on in this industry. They've been offering to you, first it was Facebook for free, or maybe it was WhatsApp for free. You remember when they told you Twitter was free for the first time? I don't know if you guys pay attention to those details. I like watching my because I'm a fan. And then they started offering, like in the last year or two, free TV, but only if you use their TV service. So you can get direct TV streaming that doesn't count against your data, or Xfinity streaming if that doesn't count against your Verizon package, or whatever it might be. So they're giving you more services, and they're not getting any more revenue for it. So how is that model going to work? So what you find in this part of the industry is it's all about cost reduction. So they're going to invest money like the railroad does in things that drive down costs aggressively. So as a CFO, you only ever want to talk about two things. If you ever plan to meet with one, there's only two things. You either got to talk about putting upward pressure on earnings or downward pressure on costs. That's it. If it's anything else other than that, they're not interested. That's their whole life. That's all they talk about. So it's an interesting environment right now. So this infrastructure demands constant, heavy investment, but you're not getting any more revenue for it. And really what happened when I went to Germany When I really went to Germany, it didn't really cost AT&T $10. It cost them a lot of money. They had to pay Vodafone, and I think I saw half a dozen different carriers on my phone during the course of the 2 weeks. And they have to pay those carriers those settlement charges at the end of the day. And it's a lot more than $10. So it's an interesting dynamic. So this is the money layer above the 5. So you can have the best network design you want, but if you don't address that money layer, nothing's ever going to happen for you. You'll never have a sale. So the people that are successful in driving solutions into this industry become very skilled at having the money conversation as well. They understand exactly how their equipment is going, and their protocols that they're proposing are going to change the cost structure, and they can prove it. They can describe it exactly for the customer. So if you figure out a new compression algorithm that can get more users over the same size circuit, or can help compress more users with the same voice quality onto the same radio frequencies, they have to pay the FCC for those frequencies, millions of dollars a year for a license in a city. So there's like billions that fly around to pay for these licenses. And if you can show them how to concentrate more revenue on the same cost structure, then that's critical to this chapter. That's different about this part of the class than lots of other pieces of it. Okay, so in ad hoc mode, there's no base stations. You can only transmit to each other. Most people aren't aware that you don't need like a central authority, like a Wi-Fi hotspot, in order to be able to exchange data. On an airplane, for example, one of you can set up ad hoc mode and communicate with the rest of you. So you can set it up with Wi-Fi. You don't need the plane's Wi-Fi. You're not going to get to the outside world, but you can get to like your shared drive, or you can run a chat session if you've got a tool that doesn't insist on seeing a server, or if you've got Linux, you can run the server. So you can organize yourself. So this is something that I would encourage you guys to play with. We don't have a lot of labs to kind of set it up because it's tedious, but that's because not enough people have played with it really to have good lab IDs. But this is there. It's available to you today. So this is called infrastructure versus no infrastructure mode. You also have an idea of the number of hops. So with a single hop, you connect directly to a hotspot. That is 90% of the time what we do, maybe 99% of the time. So we usually work right here. Most of the communications we have wirelessly happen in this top left box. You can have, and we'll see in the packet headers, there's a built-in ability to have multiple hops. So when we look at how we've modified Ethernet to send things along between wireless nodes, there are actually more fields to keep track of. The user went first to this hop, then they went to this hop, and then they finally got on a landline down below. So it's sort of weird. Okay, there's some really cool algorithms in wireless. It's the most error-prone medium that you can have. I know of no other that's more error-prone, particularly in the unlicensed spectrum, but it also applies to the licensed spectrum. There's nothing to prevent interference from nature, and there's very little to prevent interference from other man-made objects that are not intended to be communications devices. All kinds of motors, all kinds of things like alternators generate magnetic fields, generate radio spectrum, but they're not prohibited because they're not built for communications. So you must accept the interference that they generate. And then there's just interference from the fact that the FCC will give you a license for a certain area, but it doesn't guarantee you that you won't be able to hear the next one over. So has anybody ever listened to a radio station until they've gone off the air? Do you guys even have this experience? Most things are 24 hours a day. And when it does, you hear another station on the same frequency, like in San Antonio. So when I worked at Rice's radio station, when we would go off the air, we could pick up the station in San Antonio. It was very weak, but it was legal. They were doing things legally. So what you want to make sure of when you license these things is that you're given a license to where your signal-to-noise ratio compared to the other person's signal-to-noise ratio at the boundaries of your legal transmission radius is high enough, the ratio of yours to theirs is high enough that a typical, inexpensive, imperfect, mass-made radio will pick your signal out from theirs. That's the only thing they're interested in guaranteeing. So you'll find on television networks it's much harder to do because the signal is much denser. There's a lot more information. So you'll find the FCC will usually never license an over-the-air television station in two adjacent cities, big cities even. So Dallas doesn't have any of the same channels that we do, neither does San Antonio, neither does Beaumont. You have to go to like Abilene or El Paso or Oklahoma City or maybe New Orleans to find the same channel numbers used by two different TV stations. So that's the way it went. So again, the important differences for wireless are the signal strength does decrease. You have interference from other sources. And then the last one is just most easily explained by drawing something. So suppose you're downtown and U of HD has a radio tower from Verizon on the roof. So there's a cellular antenna, those tall, thin ones that we saw yesterday in some of the pictures. And you're straight down, that's not Main still, maybe it is still Main, you're just straight down the tracks, and there's tall buildings on either side of you. And you are trying to send a cell signal. And we've already talked about how what you're really sending is this ever-increasing sphere of energy. And every millimeter greater radius for this sphere, the greater the surface area of the sphere. And the energy that you've imparted to transmit the signal gets weaker per square millimeter on the surface of the sphere because it has to cover, the same amount of energy has to cover a sphere that's getting bigger and bigger and bigger. And so, of course, if the sphere has the same total amount of energy, even if you ignore signal degradation from distance, there's less of it just from the surface area equation. Right? So if I tell you you've got a bucket of paint and you're going to paint a ball, okay, great, you paint a ball. Now if I tell you the ball is twice as big and you have the same bucket of paint, you can still do it, but you may have to add some thinner to the water, to the paint, like water, for example. And if I tell you the sphere is 100 times larger, like the diameter is 100 times bigger, it's going to be like rose-colored or blue-colored. It'll be like see-through. The paint will be so thin. That's all that's going to arrive at this tower. So this has to be able to pick your signal out. So signal strength alone is not sufficient. And we're all using the same frequencies. So there's a different scheme that we're going to have to use to allow the network to detect the signal that you're sending. So the first thing we're going to do is convert it to digital so we can play with it. And we can encode it in different ways that are perhaps more immune to being interfered with or confused with other signals. So none of that's multipath yet. So what multipath gets you is, at the same time, you can draw a line that connects a point on all of these spheres that runs all the way, why the heck isn't this drawing anything? That runs all the way in a straight line directly to the tower. So if I keep drawing these bigger and bigger circles, there is one set of vectors, very narrow, that cover the height of this radio. The radio is not a point. You do have some surface area for the antenna. So you can draw a line directly from your radio to here and one to here. And each of these is a little bit of micro power, and they accumulate. Right? So if you can cover this whole thing, this represents like a patch on your sphere. So you can figure that out. Here's the problem. There's also a vector that's going in this direction, right? And it bounces off the mirrored glass on the side of this building. And a copy of that same signal shows up also at the tower. And it's exactly the same signal. It's a tiny bit weaker because it had to go this extra distance, right? You can draw a right triangle here and calculate the extra distance it went, but it shows up just a moment later. And you're going to have to eliminate that and ignore it and only pick the first one. And then there's another one that bounces off here, and here, and here, and here, and thousands of possible interferers. So the signal can take multiple paths to reach the destination. And this is called multipath interference. So if you've ever driven down the high-rises in Houston listening to the radio, and you hear what sounds like it's stuttering, and you're picking up copies of it, it's called picket fencing, because the signal's coming through the gaps in the buildings, and copies of it are arriving from different places. So your radio is constantly trying to realign to the carrier. So this is a profoundly difficult problem, and it's why I give thanks that I'm not an electrical engineer, because this is like totally a different career path. You would not be able to know both of these things very well. So the SNR is the signal-to-noise ratio, and what you're trying to do is make sure your signal is detectable over the noise. The better the electronics, the smaller this ratio can be. So I can spot, you have a really good SNR ratio. If you're in a big crowd and somebody says your name, you hear it. If they say anything else, you have no idea what they're saying. But you can pick your name out when somebody says your name, because you're tuned. You have a good SNR filter for that. And then there's bit error rate, which is another complication, which is the data is weak when it arrives, but it's also corrupted when it arrives because it's been subjected to errors. So things that were ones are zeros, and things that were zeros are ones. Qualcomm Corporation out of San Diego, I think, for their headquarters, they did a lot in this area to come up with new math algorithms that allow you to still recover useful data from a corrupted, low SNR signal. You can still pick stuff out. And so their technology is used in most communication systems. So they've been running some ads in the last few weeks that basically claim this, and it reminds me of BASF, which is a company that makes chemical ingredients like carbon black that are used to make all of your PC plastic black looking and things like that. And so they had an ad for a while that said, you know, we're the company that makes the things that make the things you use. Something like that, you know, like one order of removal. And Qualcomm is one of those as well. Okay, so hidden terminal problem is a really famous one. This is what Hawaii dealt with their Aloha network. You have two senders, and they're trying very hard to not interfere with each other. They're trying to be polite. They won't both talk to the teacher at the same time. So this would be as if we had a steel wall separating two halves of the class, and both of halves could see me. And if you wanted to ask a question, I tell you just to ask a question whenever you have one. So you'll be careful not to interrupt other people on your side, but you have no idea what's happening on the other side. You just can't hear them at all. So what I get may in fact be a collision. Two of you may talk from different sides. So that's called hidden terminal problem, where A and C cannot avoid conflicting with each other because they can't even see each other. So think about a giant Mauna Loa volcano in between two campuses of the University of Hawaii that are both trying to signal something back to Honolulu, and they both have a radio path to Honolulu, but they don't have a good path to each other. So the Honolulu site is going to be seeing collisions. There's nothing they can do about it, unless you want to give people permission. If you make them wait for permission, that's fine, but that's the whole thing they were trying to get rid of, was giving people permission, so that you could use the whole network whenever you needed to. So the signal attenuation is another kind of common issue. This one's much more common with Wi-Fi. You may be at one end of the usable radius of signal that will allow you to still hear the base station, and so you can barely get a connection. So let's say you're in Meyerland Plaza. I don't know if anybody's been over there, and you're at Beck's, which is adjacent to a Starbucks, and Beck's is like a hamburger place, and they have no Wi-Fi at Beck's. But if you sit in the row of tables that abut the wall that is shared with Starbucks, you can suck free Wi-Fi from the Starbucks place, right? So you're at the edge of the signal there, and then somebody else could be sitting on the other side at the dessert place doing the same thing. Both of you can see B, but neither of you can see each other. And that's not because there's an obstruction between you, but because you're at a distant way. So remember this, because we're going to have a simulator in the homework that I'm going to give you later today, and I got to figure out how to not like gang up on you too bad with homeworks here, especially since it was my fault I was a day late. But there's a really cool simulator, and I'll bring it up and show you guys what it looks like, that shows how this works. And so the protocols are actually quite interesting that you deal with in Wi-Fi in particular to simultaneously operate a network where some of the users can see each other and some of them cannot. So you have all these pairs of senders, and each one of these potential senders has some subset of the other senders that they can see, plus they always must be able to see the base station or they're not connected to that Wi-Fi network. and you have some that are excluded. And your protocol has to deal with detecting collisions and avoiding collisions, really, if you want it to work. So CDMA is a way of encoding a signal in a wireless network that assigns codes to users, and then that code is used to generate signals. So remember when we talked about CRCs, where you take a long piece of data, you add something to it, you have a generator, which we would normally call the divisor, that's agreed upon ahead of time, and you come up with your signal and you have a remainder at the bottom. So this is what you send. Right? So everybody has a different input. Everybody can have. So this is the type of code that is assigned to each cell phone. When you connect to the tower, you can have a code that you're going to use to encode your signal. You'll use the same frequencies, the same signal strengths. You'll have the same problem to send. You may have the same data, but you're going to not encrypt it, but you're going to encode it. It's not the same as encryption because you want people to be able to pick it out. So this encoded signal is a result of sending your original data plus what is called this thing. It, of course, has a new name. We can't use the same code names we've used on anything else. They want to have a dictionary of acronyms as well. So this one is chipping sequence. And then when you decode it, it's a very interesting inner product problem. So let me show you an example of this. And I'm going to zoom this up a little bit for this part so it's hopefully takes a little bit more of your screen at home as well. I'm not sure what it looks like actually when I do this for you at home. So here's my sender. They have data to send. They have a -1 and a 1. So the first thing you'll notice is they've created some distance between the zeros and ones. And they're going to use polar opposite values of whatever they would use to encode this. So that's a signal to me right there that they're expecting detection problems. If you create more separation between signals, it's a sign that these things can be interfered with and they might get close enough to be where you can't tell them apart from each other, indistinguishable. And so that's when I start seeing hints like this, I'm starting to think, I wonder if this is a wireless network. Okay, the other thing you'll notice is that your chipping sequence, your code, is a lot denser than your data. So there's lots more of these encoded values here, 1, 2, 3, 4, 5, 6. There's 8 of them per bit of the user's data. So that tells me I'm intentionally slowing down my transmission rate of data to give a better chance of overcoming what are probably errors, bit errors that can occur, like little burst errors like this. So if you study as a bench engineer the rate of errors and you see that errors are generally going to be about this long, then all you have to do is stretch your data signal out and you'll be able to recover from it. If you measure data signal, but clearly the technology can send bits at a much faster rate, at least 8 times faster. So this is a very common technique in transmitting data. You will intentionally slow down your data transmission rate in order to have a more sophisticated encoding of the data. Okay, so what I'm going to do is multiply these two together. That's right after I erase all this garbage. So I have my chipping sequence is 1, 1, 1, -1, 1, -1, -1, -1. So that's it. So when I see that somebody wants to send a 1 for data, then I leave this alone because this block times 1 equals itself, just like every other number. Any number times 1 equals itself. So we're going to use this for this sequence. The other value I can have is a -1. So anything times a -1 is the inverse of itself. So this is the same chipping sequence and the inverse of the chipping sequence. Are we together so far? All right, so when I want to send the -1, I'm going to flip this upside down, which is what's happening here. And when I want to send a 1, I leave it alone, which is what's happening here. So this is what actually gets transmitted over the wireless carrier. And when I get to the other end, I can suffer a fair amount of error and still pick the signal out. But that's not why we did the chipping sequence. We have other ways of making sure you can encode the signal and get errors out. Like, for example, tell me a couple of things we've done. Tell me some things we've learned this semester to recover from or detect errors in a signal. What are some of the techniques we learned earlier before we got to the wireless chapter? Checksumming, parity, remember parity, CRC, all kinds of schemes we can use. You can repeat the data, you can encode it 2 different ways, you can send it over 2 different carriers. What some companies will do is they'll send data over both sides of a connection at once. What the space shuttle did when it was first, and I had a summer job at NASA when I was at Rice, and the space shuttle had 3 IBM mainframes on it. They were stripped down to not weigh so much. They had 3, and they each ran the same software on, you know, what jets should you, from which jet nozzle should you expel gas in space to rotate the space station for its next approach to a satellite, for example. You don't want to screw that up, right? You don't have an infinite supply of fuel. And it's not like burning fuel. This is not like when it's launching. This is just to orient and move you. So these apparently were error-prone algorithms, or I never really got an explanation that I thought made that was acceptable. Let's put it that way. So they used a 2 out of 3 rule. Believe it, they ran the software, and they would take the action that 2 out of the 3 mainframes said to take. So they were expecting it not to agree. Can you believe that? Can you believe that? This would be like being in open heart surgery, and you're trying to figure out, you know, whether to cut a vein this way or that way, and one way will lead to death, and the other way won't. And 2 of the surgeons think it should be this way, and the 3rd one says, no, don't do it that way. Or you're in a landmine, you're trying to figure out whether to cut the red wire or the blue wire, right? So it's mind-blowing to me that it worked that way, but it did. Okay, so the received output is just the opposite. You receive this thing, you go through pattern matching, and then you'll crank out the same data. So I said this isn't why we did chipping sequence. Here's why we did chipping sequence, because there's more than one user at a time. So now let's look at what happens. It's 2 different data streams, a -1 and a 1 followed, and the other user has a 1 and a 1. So they're sending different data, and they each have a different chipping sequence. This one's the same as the slide before, but this guy has a different one. He's using a different cell phone. And so they're both going to be sent over the same frequencies and received by the same radio. So you're going to have to try and figure out what's going on. So we're going to run through this exactly as we did before, but now we're going to do it for 2 users at a time. So here's what happens. I know that when I had my first signal times a -1, I'm going to, if this was my chipping sequence, I'm going to invert it, right? We know that. So that's what I'm going to do. I'm going to turn this into the following. -1, -1, -1, 1, because this one gets inverted, and then another -1, and then 3 ones, right? So far, so good? I'm going to look down here. Here's this guy's chipping sequence. He's trying to send a 1, so I don't need to invert his chipping sequence. So his chipping sequence needs to be sent just as it is. So which is 1, -1, 1, 1, 1, -1, 1, 1. Add the columns up. -1 plus 1 is what? 0. -1 plus -1 is -2. This is a 0. This is a 2. 0, 0, 2, 2, which is exactly what we're sending. Now, one of us did something funny here. I guess what I just went through was this one here. So let's see if it's right. 0 is here. -2 is here. This is a 0. 20022. 20022. It works. When you get it at the other end, all you do is you pick one of the chipping sequences and you subtract it from the value, and you should be able to recover your signal out. And what's left should be the other person's. So this works for an arbitrarily large number of senders and is one of the more brilliant things that makes cellular communication possible. So hopefully for some of you, you're like, right? Because this is sort of like, I had a student a few years ago, and I don't remember why we were staying so late or something. I think it was an exam, and there were like 4 people that stayed till the bitter end. Everybody else left early. And I said, come on, I'll buy you guys coffee. And so they were friendly. We go over to the place on the other side of Cougar Place over there, and one of the guys was from overseas, and it was new, he had not been to a Starbucks or something, I guess. Anyway, they had a special on iced coffee, and he just couldn't wrap his head around it. He had never heard of iced. He was a really sweet guy, and I'm not making fun of him, but it was really funny. And so the clerk says, "Yes, we have iced coffee." He did that to the student, and so we all kind of laughed and stuff. And he was like, "I've never heard of that before." So it was a good experience for us because you learned something about another culture. But this is hopefully one of those moments for you guys as well. So for wireless LANs, better known as Wi-Fi, there's a variety of standards, and you guys have seen all these letters, and you try to figure out what the alphabet soup is, but they all use a type of CSMA. And if we go back again, CDMA is what this is. CSMA is different. So this is Carrier Sense Multiple Access. Where else have we seen this acronym, CSMA? Other types of multiple access, more than one user on a network have we seen? Where you listen to see if it's available before you send something. And if it sounds like it's available, you go ahead and send your data. What's the world's dominant wired technology for LANs? Okay, we're gonna have to do it this way. You guys know Hangman? We're going to play it if you can't get this. I'm going to keep an eye on the chat window. Nobody out there? No one? Okay, well, so we're going to play Hangman. Give me a letter. No, no A. I? No, no I. What? E? Yeah, E. Yep, there's an E. What's that? Ethernet. Ding, 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 ding. All right, very good. So, and if you don't know what Hangman is, come to me afterwards. It's actually fun. I just have no concept of how global it is. It's something I know, but I don't know if anybody else around the world knows it. Okay, I pulled in this standard from the IEEE site. I was wandering around on there yesterday reading some papers and things, and I thought I'd throw you guys a little different looking table. This is also there's an online version of the 7th edition of the textbook. I don't know if anybody's seen it, but you can rent the textbook digitally, and they gave me access to it, and I think the table actually came from there. So with this LAN architecture, you have some terms that you and I don't ever use, but which are important to understand how it works. So the first one is a basic service set. So this is what we would call a cell. So BSS in infrastructure mode is something you can draw a circle around that contains all of your wireless hosts, your access point, and that comprises the basic service set. And if you want to connect these things together, then there's other terms for how service sets work with each other. We would basically call it finding the SSID in your drop-down list of networks and connecting to one. That's all we would call it. But there's different terminology in the field. So you've got multiple channels, and then you associate with them. One of the more fascinating things that I don't know if we'll dig into much here is Wi-Fi, like a lot of current technologies, ones that have been invented and will continue to be invented, are spread spectrum technologies. Anybody have a guess what that means? So let me go at it a different way. When you look at the spectrum chart from the FCC, do you guys remember how we looked at that? Anybody remember that one? It was, see if I can find it. Here we go. This is old, but it's still okay. It's from 2003. So let me share this. Da-da-da-da-da. Was it Chrome or was it Firefox? No, it was neither. It was Adobe Acrobat. Okay. Do you see a lot of free space on here? No. And in fact, the only way you're going to deploy a new technology is by either stealing from someone else, taking it away from them, or sharing it with them. So taking it away is usually a non-starter. That's hard to do. Now, there was a lot of waste, and there still is waste, but in order, like, look at this for AM radio. I mean, how many people listened to an AM radio station in the last year? even for a second. Yeah, exactly. So why don't we go after this? Why aren't we aggressively trying to grab the signal? So is this a lower frequency or a higher frequency than the rows below? Lower. And what's an inherent drawback of trying to communicate with lower frequency spectrum? Data is slower, right? You can't get as much across it. So what about the ability of this signal to make it through lots of common construction material? Like, can you listen to AM radio inside your house? Sometimes. Depends on whether you have mirrored glass, which windows facing the west and the south by law are supposed to have a semi-transparent coating, low heat glass. Sometimes in buildings you can't get through it. So it's just not very valuable to us. That's why we haven't gone after it. But what we did 20 years ago was we made everybody, maybe not even that long, get rid of their television sets. We stopped broadcasting the way we had for 80 years. And people had to get new digital receivers because we were squeezing some of the bandwidth out of broadcast television. And so we forced them to do it. Somebody told me, and one of my students in Mexico told me that Mexico stopped completely over-the-air broadcast, but I looked at their spectrum and they still have it. So this is more valuable because you usually can get a television signal inside your house. So it's higher frequency. It also means you can encode more data. So the problem with these things is there's a sweet spot in this chart for what you want to use for communications. And also the higher you go, wow, that was kind of cool. I wonder if I can get it back again. It's my first time using Adobe Acrobat. How does it keep doing it? So the other thing is the further down this you go, the more expensive it is to build the equipment because it costs more to build equipment that oscillates faster. It uses more power. So things down here like Earth exploration satellites and radio navigation for airplanes, and there is a broadcasting channel in here, mobile satellite, etc. These things are not things that we typically will use, but there are some. So you start seeing in here all these little pockets of pink called mobile. Do you see them in here? There's one here. There's one here. So what you're going to do is find a and you're going to share them with someone else. And the reason why they don't use this one, well, we can go and look and see why this guy lost and the other one. And this one is space research, and this one was fixed point wireless, which basically means a little point-to-point signal. So fixed point wireless usually means you're aiming directly between 2 points. So that's a very small channel over which this communication stream, and you can tell them, you can make it harder on them, raise the price, and make them go, buy a circuit from the telephone company instead. But here's space research. You probably have the elected officials that represent NASA and some of the states that have big space research things lobbying not to do it. So which layer is this going to get decided at? Politics. Okay, this is the politics layer. You will group together ones that you can, and what we did for Wi-Fi is we picked 13 frequencies, and they're built into all Wi-Fi stuff. The problem is this chart doesn't look exactly the same around the world. It looks largely the same, but not exactly the same. And we'll talk a little bit more about that as soon as we pause the recording for a moment so we can get an hour recording out of it, and then I'll be right back. Stop recording.